Going over here today is all the basics of our first lab. So, lab one, we're dealing with chromatography. We're dealing with TLC, thin layer chromatography, and we're dealt with column chromatography. Okay, so let's talk about the basics of TLC. In TLC, we had a plate. Now, if I look at the side view of the plate, okay, I had a silica backing. So let's make that just green for just funny or fun sake. And we'll say that that green backing, we won't say, but it's definitely due to a silica. Now that silica is basically silicon, or the element silicon, uh, and it's bonded to some oxygens that have some negative charge to them. Okay, and you probably have some sodiums in there as well. But the bottom line here is that what we have is a very polar area. We've got positives and negatives that are on the outside of the plate. So we would say that in chromatography, if you know the basics, we're trying to give the mixture, which if you remember is a universal indicator. Now the universal indicator is a mixture of three different indicators: phenolphthalein, methyl red, and bromothymol blue. Now a mixture, and this is another piece, is not bonded. It's just physically made. So we can separate it physically. So chromatography, whether it's column or TLC or column, is a way that we can separate this mixture based on its physical properties, and one of that is solubility. So these two techniques are using the property, the physical property of solubility. Now, solubility, okay, is based upon the type of attractive forces that chemicals have for each other or other chemicals. So back to my silica plate, this is a polar, very polar plate because of the silica. Now, what does that mean? Well, that means that the attractions that other chemicals are going to have for the silica are also going to be polar or dipolar. Okay? So polar attractions, that means something with a what? General positive or negative end is going to attract this end. So something that has the same type of or similar polarity would very much stick to the silica gel. So the attractive forces of something that like silica gel will mainly be the very strong H bonding, as you might have learned, or the dipolar forces. Dipolar forces are just polar molecules with a partial positive and a partial negative. Okay, so you learned probably somewhere in your chemistry life that like dissolves like, although that's not always perfect and best way to explain things, but very similar attractive forces. Any case, so in my universal indicator, okay, the parts of the mixture that are very, very polar, okay, are going to like the silica backing. Now, in a TLC or thin layer chromatography, we're going to put this plate, okay, and put a solvent in this plate. So we're going to put a solvent here. Now that solvent, in this case, if we're going to use silica, which is, my friends, a very polar, okay, part of the plate, the solvent, we're going to use something that's generally more nonpolar. Now, why do we do that? Well, we want to give the mixture in the universal indicator a choice to either stay with the very polar backing or move with the nonpolar solvent. See, the nonpolar solvent is going to be pushed and pulled up the plate by capillary action. Now we have atmospheric pressure pushing down on the liquid, and we also have some attractive forces that are pulling some of the solvent along. Now in the solvent, party people, we have two things. We have hexanes. Now, what are hexanes? Hexanes are essentially hex, meaning 6 carbons that are straight chained. And of course, the rest of the H's, these are hydrocarbons, very, very saturated. And as we've already learned, that while this is very symmetrical, yes, however, a carbon to hydrogen bond, as all the rest of these indicate, are generally nonpolar bonds themselves because of the difference in electronegativity. So no matter what the shape is of a hydrocarbon, hydrogens and carbon, okay, they will have no polarity. So hexanes are nothing more than 6 carbons that are single bond, and they could have a very branched, okay, structure as I'm drawing here, 1, 2, 3, 4, 5, 6. So this would also represent hexanes, although it would have a different IUPAC name. It's also nonpolar, even though it's little asymmetrical. The carbon to hydrogen bond is considered to be nonpolar because the difference in electronegativity is very similar. So we have a very, very, very nonpolar part of our solvent. Now we mix something called ethyl acetate, okay? Now ethyl acetate looks with something like this. Let me change my ink. All right, we had 2 C's, and then we've got this this kind of compound here at the end. And I think I just messed up. Let me try that again. So ethyl acetate is an ester, and let me just try that one more time. So we have the ethyl from the alcohol group, as you remember from your organic chemistry maybe. And then we're going to have the acetate and acetic acid, if you remember, looks something like this. So we're going to push these together, and what you're going to get is a carbon double bonded here, and then your CH3. The bottom line here, whether you know the structure or not, ethyl acetate, okay, is an ester, and esters are aromatic, and you could probably guess they have some level of what? Polarity. So there is some polar behavior. Now you would say also that they also would have something called London dispersion forces because they have places where you have a nonpolar area. So they would also attract to the hexanes because they are a little bit nonpolar in character. They'd have London dispersion forces. Hexanes, as you remember, are all nonpolar, so they would have London dispersion force, or LDFs if we're cool. So the hexanes will mix and have some miscibility with the hexanes. However, they have a little bit of polarity, and that's important. So our solvent is going to be hexane with ethyl acetate, and that ethyl acetate's important because it gives a little bit of polarity to my solvent. Why is that important? Well, what's going to pull the liquid up my plate? Well, the silica polar ending is probably going to pull on the polar ending, this asymmetrical part of the ethyl acetate here. All right, and if that happens, we can better get the solvent up the plate. Okay, so the silica will probably pull and attract the ethyl acetate in the solvent. The ethyl acetate will probably pull the hexanes along because they do have regions of nonpolarity where they would similarly have attractive forces for themselves, which, by the way, again, are LDFs, the nonpolar attractions, or those London dispersion forces. So in any case, we've got a solvent that's mostly nonpolar. It has a little bit of polarity, but mostly nonpolar, and we've got the solid part of the plate to be polar. So what do we have in chromatography? We have 2 things. We have a stationary phase, and let's write that. So we have a stationary phase. So our stationary phase in this case is the silica. And then we have the what? The mobile phase, which is the nonpolar solvent, okay, mostly. So we're giving the mixture a choice. When the solvent gets pushed up by capillary action, we're giving the mixture, and we spot our plates accordingly, little tiny spots, we give the mixture a choice to either stay with the silica or move with the solvent. So if in fact there are differences in the polarities and the percentage of polarities, because big, more advanced molecules are never going to be polar and nonpolar. They're going to have some subtype of percentage of both, just like the ethyl acetate has some nonpolar character to it and some polar. The ones that are more polar will probably like the stationary phase here because it has a polar backing, which means like dissolves like, and it will stick to it and it won't be able to move up. The ones that have more nonpolar characteristic are going to like the mobile phase and not prefer the silica and move up the plate. So when we separate them, we're going to have different amount of movement up the plate, and you're going to see that. And we're going to measure this difference, which is called rate of flow. It's called the RF factor. So we're going to measure how much they move. Now the ones that move the most like the mobile phase because they probably are what? More nonpolar in character and have more in common LDF attractions than they do with the what? Polar attractions. So that's very important you understand that. And we can measure this movement, right? We can measure how far the solvent moved, okay, called the solvent front, because this solvent's going to move all the way to the top. And we can measure how far it moves. In fact, we probably measure it from the bottom here. So how much it moves compared to how much the what? How much the individual parts of the mixtures move. They're all going to move different lengths. So we start with one spot, but then we might get eventually a reddish spot that moves farther. And then we might get a spot we didn't see in the middle, but eventually when we spray it with phenolphthalein, with a base, maybe we'll see the others. So they're going to move at different lengths, and we can measure something called the rate of flow, and we can look that rate of flow up and figure out what the chemicals are. Okay, so TLC is basically what I explained, the basics of chromatography. All right. Now, column chromatography uses the same scenario, except in column chromatography, I'm using a column and a syringe. And the column that I'm using is something called a set pack. But it doesn't matter what it is. In industry, it'd still be a big column. And in this case, the set pack has a C18 compound. And C18 is just another carbon that has 18 carbons bonded, single bonded, and it is also an alkane and very saturated. And of course, because it's a hydrocarbon, it's essentially nonpolar and only has LDF forces. So we're going to use a solid, or in this case, our solid phase is predominantly going to be nonpolar. Okay? And we're going to eventually push our universal indicator, okay, through the set pack. Okay, and basically we're going to do that with the solvent, okay, that's already in there, the same solvent that is in here, and also with the universal indicator, we're going to push the solvent through. Now the solvent, okay, is going to be pushed with the universal indicator, and we're going to give the universal indicator choice to either stay with the C18 if in fact you have what? Nonpolar characteristics, or go with the solvent. You may say, Mr. Grodsky, isn't the solvent pretty much nonpolar? Yes, but if you remember, there's a what? There's a, I can't move this, there's a ethyl acetate or what? Polar characteristic in here. All right, so any case, our solvent's mostly nonpolar, but it does have a nonpolar characteristics. So what comes out first? Well, the ones that like the nonpolar C18 would probably stay last, and the ones that come out first probably like the polar characteristic, or the, even though it's a little bit, remember we're giving the chemicals a choice. Stay with the solid phase in this case, which is nonpolar. It's flipped on its head. TLC is different. Or go with the more polar solvent. And the chemicals that come out first preferred the mobile phase or had similar what? Attractive forces. The ones that came out last in your test tubes had what? Well, preferred the solid phase. So both of these tests should confirm, but don't forget column chromatography, column chromatography, all right, is going to prefer, the column is going to be different than your TLC. The column, all right, has the nonpolar what? Solid phase, where in TLC, the solid phase was the silica, which was the polar phase. So you have to make sure you understand that. So you're confirming your hypothesis by the movement up the plate and determining who is the most polar and nonpolar in the TLC, and you should get the same results understanding how the solid and the what mobile phase are flipped here in the column chromatography, meaning the one who moved up the farthest in the plate must have liked the mobile phase, which was mostly more nonpolar than the silica, right? And the one who left the column last preferred the more nonpolar solid phase, which was now nonpolar. Both of these tests, or in this case chromatography, should give you the same results if you understand them. And now you can see if your hypothesis of which chemical was the most polar or nonpolar, okay, works out. Hope that helped.